today, super guest on the History Podcast, Joe Powell from Akron Steel Trading President. And before the podcast, he told me that he's been around for some time and has designed some interesting stuff. And today we're gonna talk about quenching in general. Joe is a quenching expert, a furnace expert, a heat treat expert, and he actually was the one that brought the subject about quenching. So we're gonna cover the basics. We're gonna go on different quenching mediums, their pros, their cons, and we're gonna go deep into it. I'm pretty sure I decided to talk to you, Joe. So, Joe, how's it going all the way to Ohio?
Oh, it's wonderful. We had some thunderstorms yesterday, but today it's partly sunny. And my daughter's here from Canada. Her and her husband have a business in Sarnia, Canada, and they're home on their way to South Carolina for a vacation with her sister and the kids. And so all four grandchildren and two great nieces were here last night for a birthday party. So Christina, incidentally, Samoji, as our Vice President of Administration at Akron Steel Treating, and went to the YES program with you, Carlos.
Is Christina in the room? I just would like to say hi really quick.
She's upstairs. We'll get her down here.
Okay, say hi when you say it. So, okay. Joe, can you just tell us a little bit about your background, your involvement with heat treating, and a little bit of Akron Steel Treating?
Well, Akron Steel Treating was founded by my father, Prosper Paolucci Powell. He came to the United States when he was 3 years old, and in 1928 went to work for Firestone Tire and Rubber Company's Metal Products Division in Akron, Ohio. And he headed up the heat treat department in the 1920s and 30s. And in the 1940s, he had an opportunity to start a small tool and die heat treatment facility in the family's garage in Akron, Ohio. And from that grew Akron Steel Treating, and from that grew a company that my brother joined when he got out of the Army in the 1960s. My brother's Ron is 18 years older than me, so it's actually like I'm the third generation of Akron Steel Treating, and Christina would be the fourth generation of Akron Steel Treating family members. We do a wide variety of heat treating. We have vacuum furnaces. We have controlled atmosphere furnaces, and we also have salt bath furnaces. And it is that salt bath niche that really got us into doing a lot of aerospace wheel and brake parts for airplanes back in the 70s. Actually, it was back in the 60s, because the salt quench does not distort the parts. And there's some very critical parts in airplane brakes. They're called keys that locate the rotating discs and the stationary discs in an airplane brake. And these keys are kind of a U-shaped part, and they're kind of long and skinny and thin, and they turn into a pretzel if you don't quench them properly. The other thing is, instead of martensite, they want bainite, and they want that bainitic structure that Chip Keogh and Applied Process is so fond of touting. That bainitic structure in the metal has a great combination of hardness and ductility. And so you combine the right hardness, the right ductility, and the lack of distortion, and salt quenching, which everybody says was, going to go away, has not gone away, and we're still using it to this day and do quite a bit of salt quenching.
Actually, salt quenching is getting popular at the moment as we speak.
To control distortion. Yeah, that's correct. So in any event, we do work for approximately 300 different part makers a month that bring us products. We have one or two part numbers that are for automotive, and the rest of it is either aerospace, tool and die, or parts for construction and mining equipment. So we're not heavily automotive at all, although there is one part that we do, one set of part numbers that we do for transmissions that there really isn't any other way to do them except in salt to salt. About, well, it's about 1997, I was introduced to Dr. Nikolai Kabasko who was from the Ukraine, and by Dr. Michael Aronoff. And in 1997, Michael Aronoff called together a group of heat treaters in Cleveland. It was John Vanis from Euclid Heat Treating, Wayne Samuelson, he was then the owner of Shore Metal Treating, and myself. And we went up to where Dr. Aronoff was working, which was the American Gas Association Research Labs. And at that time in 1997, there was a big push to use some of the monies that the American Gas Association Research Labs received from each cubic foot of natural gas that was sold. Some of it was earmarked for R&D, how to use natural gas for different things, as well as how to make all of those different things more efficient and more environmentally friendly and safer too. They didn't want gas appliances blowing up either. So that was what the AGA labs did. Michael was a thermodynamicist who got his doctorate in St. Petersburg, Russia, and came over to the United States in 1988 and with basically $400 in his pocket, and began trying to make contacts in the industries that used a lot of natural gas. And of course, heat treating and Northeast Ohio is kind of a hotbed for heat treaters. And so he proposed to use a technology that he became familiar with working with Dr. Nikolai Kabasko back in the former Soviet Union, and it was called intensive water quenching. So when he called this meeting, we were in this big conference room at the American Gas Association Research Labs. And I'll never forget that he invited the dean of the College of Metallurgy from Case Western Reserve University in Cleveland to attend this meeting. And he brought with him a postdoctoral student from China that was working to get his doctorate, or working on his doctorate, I guess, at Case. And Professor Jack Wallace was the name of the gentleman that was the dean of the College of Metallurgy. So Michael goes through this spiel about how he wants to demonstrate in the United States this intensive water quenching technology. And about 20 minutes into the meeting, after all the introductions were done and it was explained what he was trying to do, Jack Wallace, who was probably in his late 60s at that time, leans forward and he goes, "It'll never work. Parts will blow up in the quench. Can't do it." and Michael's just stunned. The heat treaters in the room, myself and Mr. Vanis and Wayne Samuelson, we all kind of looked at each other and said, "Well, this meeting's over."
you know about what you're saying, heat treaters, especially when you're talking into that level of technicalities, especially metallurgists. I don't know if the gentleman was a metallurgist. They get very passionate about the discussion, right?
Yeah.
What happened then? It's a great story. Go on.
Well, we kind of looked at each other, and then the Chinese postdoc student taps Professor Wallace on the shoulder and said, "Yes, Professor Wallace. Yes, Professor Wallace." And that was it. And Michael kept on with his spiel, and then he basically said, "All I really want is the American Gas Association Research Labs are going to build this 500-gallon test unit to my specifications, and we will just need one of you 3 heat treaters to heat some parts up in an atmosphere furnace, and then we'll quench them in this unit." And so, and we're planning to do 50 to 100 bearing steel. It's a non-carburizing through hardening bearing steel.
Mm-hmm.
And then of course the heat treaters and Professor Wallace are looking at each other saying, 52100, man, that's awful crack sensitive material. It's deep hardening material. It's got 1% carbon in it. My God, you can't quench that in water. It'll blow up.
Right.
And so I'm sitting there thinking, well, if all he wants me to do is heat some parts up, and we have a little tool room atmosphere furnace where we could heat them up, and if he wants to wheel in this 500-gallon system, we can certainly accommodate him and do the tempering afterwards. So let's try it. So about 6 months later, this unit shows up because John Vanis and Wayne Samuelson basically thought, like Professor Wallace, that there was no chance that this would work. And we heated up about an 8-inch diameter tapered bearing ring made by a certain bearing company very close to here, and made out of 52100. And we heated it up. And at this time, we invited Professor Wallace to come over and witness this test. So we're all standing around as this ring comes out of the furnace red hot, and then was put on a platen, and this platen went down into a tube, and it was kind of like a drinking fountain with about a 6-inch plume, 10 inches in diameter of water coming out. And as I learned later, it was about 1.5 meters per second of flow. So 5 feet per second of flow past this ring. And basically the part went into the red hot part went into the water. There was no boiling, no steam, no sound of water boiling. And in a few seconds later, the part emerges. It's wet, and then all of a sudden it flash dries as the core heat in this ring self-tempered the martensite that we had just formed several seconds ago. And what we learned from this is, one, the part didn't blow up. And what we learned from it a couple years later is why the part didn't blow up is because when you quench a part that uniformly, just like in a salt quench where there's no film boiling, there's no nucleate boiling, there's no different cooling rates in a salt quench. It's just that salt impacts the surface. It pulls the heat out. It forms a martensitic or a bainitic shell on the outside of the surface. And at the end of the day, that shell pretty much holds that red hot part into its existing geometry. And so the geometry that you get is consistent because there's no film boiling going on the surface that basically is a gas quench contiguous with forming martensite grains under a water quench. In other words, wherever there's film boiling, it's a gas quench, and wherever there is water that's not boiling, it's a water quench. And so you have very slow quenching versus very fast quenching in contiguous places on the surface of the part. And that's what causes the non-uniform thermal shrinkage, as well as the non-uniform phase transformation from austenite to martensite. But once you form that shell, and if you form it uniformly, you can water quench all day long and not have parts crack. In fact, they don't crack because, as Professor Jack Wallace wrote a paper with in 1999, a paper on punches, S5 tool steel punches, you're forming compressive stresses on the surface. That martensite, as it swells up by 2 to 4%, creates a shell that's not only hard and cold over the still hot core, but it also forms a shell under what we call current compressive stresses. And those current compressive stresses act like a die that's custom made for the part and hold the part while the core cools by conduction through that shell.
So I got to stop you there. So Professor Jack Wallace, what was the expected result, or what was what he was trying to accomplish by doing that experiment? What he was trying to prove?
On the punches?
Yeah.
Yeah, he was trying to determine how it worked. because what was the mechanism that showed how it worked? And basically that punch study, I sent you a slide with the punches shown.
I mean, you want to share it?
Yeah,
You can share it.
How do I share it?
You can share screen, no problem.
Oh, I see. Okay.
So
But anyway, this is another slide that needs to be shared, and that is
will do.
yeah, we'll get to that. But anyway, what we found when we did these punches is that the oil quench punches made out of S5 material were exactly the same hardness, 60 to 61 Rockwell, but they had 200 megapascals of tensile stresses on the cutting edge, which translates to 29,000 pounds per square inch of tensile stress on the surface. And that tensile stress causes that punch to fail after it makes 400 holes, starts chipping around the cutting edge. Whereas the intensively quenched punch had 900 megapascals of compressive stress.
When you say intensive quench, you mean water quench, right? Just want to make it clear.
Intensive,
right? Okay.
No, it's not just a water quench. It's a water quench that is uniform, and the cooling rate is not like a traditional water quench. It is a cooling rate that is 400 to 600 degrees centigrade per second.
Okay, it's a process. So it's
a process.
The medium is water quench, but it has to do with flow, cooling, and specific way of quenching the part. Okay.
Yeah. Eliminating the film boiling pretty much instantaneously. You have to eliminate the film boiling and have water that touches the part and that pulls out heat energy at the rate of 400 to 600 degrees centigrade per second, and then more water is replaced and put in there and continues to pull that heat out of the shell of the part at such a uniform and intensive rate that you literally in 0.2 seconds or so form a shell of martensite. Once you have a shell of martensite, part's hard and your geometry is set. So if you don't like the geometry, then change it before you stick the part in the furnace. In other words, it'll quench to fit. The part will and we eliminate heat treat distortion is basically.
Okay, you touch a very a sensitive subject on heat treat, which is called distortion.
Yes.
Right? And you know the common thought of the quenching media, saying we got gas quenching media, we got salt, we got oil, we got water, is that water. Well, polymer, of course, as well, right?
Yeah.
But you know, saying that water is pretty severe and that parts are gonna get distorted.
Yes.
That's the first thing that comes to mind when you say water quenching. It has to be very thick stuff. It has to, you know, the geometry.
Very simple.
Very simple. You know, there has to be a lot of agitation, right? I know that some of the big constructors. Like the Caterpillars or the Komatsus or whatever, they use a bunch of water quench, right?
Yes.
But you're saying something really different here. Like we can actually control water quench, right? If we do the process right, right? Yeah. So am I getting you right?
Yeah, it's all about control.
It's all about control. And let me bring my subsequent question, because you know, I work a lot with control guys. I work a lot with furnace engineer guys, with auditors, with quality guys from you name it, from customers, internal, and all the attention, 80% of the attention goes to the process variables of the hot chamber, of the atmosphere.
Right. Yeah, the hot zone. The hot zone has to be certified.
You know, gas analysis.
Yes.
You know, what else? Redundant oxygen sensors.
Yes.
You name it. You know, infrared. You name it. They have a bunch of lights and bells in there, right?
Yeah.
And I have discussed this with many metallurgical engineers. Actually, when the transformation occurs, is in the quenching process.
Right.
And I don't believe that there even half of the gadgets and sensors there are on the hot chamber in the quench tank or quenching system,
Yep.
right?
Yep. Yep.
Let's take just an IQ or a pusher, or you name it, a furnace
Yep.
with an oil tank, right? They just
Yep.
got their agitators, they got
Yep.
their thermocouples in order
Yep.
to cool it down, or but we don't have any sensors.
Uniformity standard.
Uniformity, and it's very hard to measure those, right?
Yes. Yes.
Because every load is going to be different, the flows are going to be different, right? But, so I believe you are very close to bring something to the industry that everybody is tend to believe that is a black box, right?
Yeah. Yeah.
So
You might want to talk to the guys at SSI down in Cincinnati.
I talked many times to Steve about doing this, right?
Yeah, Steve, I actually made a presentation with Michael Aronoff to Steve several years ago about a quench probe, a quench uniformity probe that we could build. And, at that time he was getting into the nitriding controls.
Right.
And he said, my plate's full. We can't do that.
Right. I'll make sure that happens. Don't worry about it. I know
Okay.
Steve. He's a good buddy.
All right.
And just going back, also, I've known a couple of captives or oil companies that have done this analysis with, I don't know if you have seen the movie Twister. I mean, they've done it with like spheres that are measuring the flow and they want to see, but it's very hard to track and see the effects on different loads, right? And there have been some captives that I won't say names, but that I know that they've done the testing somehow. I don't know which gadget they use or what.
Yeah.
And the results that they found were horrible. And they say, well, this won't come to light because if we actually show them, we're going to be in deep trouble with our final customer, right?
Yeah, right. Because the customers don't have a uniformity standard for quench cooling.
I know there isn't one. There isn't one. I mean, and I had a podcast regarding induction, right?
Yeah.
And well, I'm more of an automotive guy. And CQI9 for induction calls that you have to measure the power, right, to heat up the heating system.
Yep.
Plus, you have to measure the flow of your quenching media.
Yes.
Right. We do not do that on quenching. On conventional quenching. I don't know if you have an opinion regarding that.
What you have to do is get beyond a certain point of quenching. It's actually a bell-shaped curve. And again, I'll send you these slides.
We'll post it.
Yeah, that you can share with your audience. But at the end of the day, once you get past a certain point, in fact, Professor Jack Wallace was thinking about quenching, seeing the curve that shows the faster you quench, the higher the probability of cracking the part. And that's true. However, Dr. Cabasco discovered that if you kept on going and went faster than what anybody had anticipated to be fast, and went to the point where you are quenching at 400 to 600 degrees centigrade per second on the surface of the part, and you do so uniformly, because that's the other thing that I've spent the last 25 years figuring out how to do it uniformly on a complex shaped part or on a thin shaped part.
Especially when there's a lot of agitation is involved for the
agitation is one component, but you also have to get that agitation to the part. And then the patent pending quenching process that I have says you got to get the water away from the part. So you got to get it there, you got to get it there uniformly, and then you got to get it away before it has a chance to boil. And if you do that and you set that shell, you literally will create a custom-made press quench die on the outside of the parts. And does this mean that you can still stack parts up, 20 on top of each other like bevel gears and stack them up on top of each other? No, you can't, because there's no way to uniformly reach the entire surface shell of that part if you got another hot part sitting right on top of it. And so rather than correcting the distortion after heat treat with grinding, we have a customer in Akron Steel Treating that makes bevel gears for steel mill drives that don't need any final grinding because our quench is so uniform after the carburizing process that water quench sets the shell. And after we essentially quenched 6 of his gears, he had dialed in the CNC program in so that the teeth actually quenched to fit. They came up across the top and were straight, and he dialed in the green sides of the part before heat treat so that it actually transforms during the quench and temper.
I gotta ask you something.
Yes.
So this coming to my mind. So you're quenching on a batch, right?
Yes.
On a big basket.
We do 12 of these gears at a time.
Now, is there a way that this could be applied on a single flow process?
Absolutely.
Because
Absolutely.
What I'm listening from you is that one of the challenges is like every batch has different shapes, right? But if you were to take out the basket and stuff and just design the quenching, the intensive quenching system only for a single piece flow, will be easier to do it by piece, and you can actually, I don't know if you can run an induction or something with a steel with a high carbon steel grade, and then just quenching. Does that ring a bell?
Oh yeah, absolutely, and we do that. We actually built a system 5 years ago, a prototype system. Under Akron Steel Treating is a member of the Forging Industry Association, and it's always been a dream of forgers to eliminate the normalizing process.
Every forging guy tells you, we want to eliminate normalizing. So how can we do this?
Well, you can do it very simply. The Japanese.
Sure, you want to state that, or you want to make a $1 billion business yourself?
Well, it's very simple, but you gotta buy this technology for me.
Right, got it.
Okay. But
if you go to this podcast and you buy something, I'm getting a % out of it. Okay.
Absolutely. Right? Carlos, you sounds to me like you're the kind of guy I want to partner with.
Oh, totally. Everybody wants to partner with me. We'll make it happen.
All right. But what is happening?
Actually, I got a couple of guys that would like to talk to you regarding that application.
All right. Well, we did a 5-year project, and we studied direct from the forge. I call it instant impact quenching, but basically direct from the forge intensive water quenching. And the way it works is you blast the forged part with so much water under so much pressure and velocity that you eliminate the film boiling after a few seconds. And that elimination of the film boiling sets the surface of the forging to the point where that part now is going to be hardened directly from 2150 degrees Fahrenheit, directly from the forged trim dies. And so what you end up getting is a part that is doesn't need normalizing because it's already been converted to martensite. And because the quench is so fast, there is a quenching dynamic that's completely different than oil quenching. Oil quenching takes about 18 seconds to begin forming martensite on the outside of the part. Polymer water quenching, same thing. There's a steam blanket that forms on the outside of the part and stays there and retards the cooling until a uniform quench can be had by the part dropping below the boiling point of the quenching. But with intensive quenching, we physically remove that vapor blanket by blowing it off the surface in like 0.2 seconds. Once the vapor blanket's gone, you now have a uniform quench just like the Ostemper quench. You have molten salt goes around the outside of the part. You can tell I'm Italian because I'm talking with my hands.
It's great for the podcast. It's a lot of attention to the video. To the guys that are hearing this on Spotify, Joey just going all nuts with his hands and trying to explain everything.
Okay. Well, in any event, once you form that shell and once you form it uniformly, and there's another slide that we'll share with your audience.
We'll share it. Don't worry.
Yeah. So once that shell has formed uniformly on the outside of the part, you're going to get that geometry predictably. And if you don't like the geometry that you got, then change it in the green size before you stuck it in the furnace. And at that point, we have literally handled heat treat distortion. Ford Motor Company told, there's a gentleman in Cleveland, in the Cleveland area, Middleburg Heights. His name is Dr. Lynn Ferguson. And back in Dr. Lynn Ferguson's company was called Deformation Control Technology. And it was a consortium of basically metallurgists and computer programmers who were going to get together and delve into the modeling of the heat treat process. Everybody said you can't model the heat treat process, especially the quenching process, because there's no way that it's uniform enough. There's no way that it is predictable enough. Well, they started out with this computer program back in 1992, and at that time, Ford Motor Company was part of the consortium. And the gentleman, I believe his name was David Dodds, who was head of Ford Powertrain, said, we spend $222 million a year in heat treat, post-heat treat correction for grinding, straightening, flattening, you name it, hard turning. That $222 million per year could be reduced significantly if they applied the technologies that we have developed in the last, basically the last 5 years. And those heat treat technologies set the shelf. And the other technology that has come out within the last 5 to 7 years is a three-dimensional cloud mapping technology that you set the part down on a platen, and then lasers come in, 2 lasers come in, and they basically, with a computer, measure this part and give you millions and millions of points of measurement on that part. They also create a model of that part that shows the volume, and you can slice it, you can dice it. And at the end of the day, those millions and millions of points of measurement can now be used to compare the part before heat treating to after heat treating. And that way, when it comes out of the quench and it comes out of the temper furnace, you measure the part, you compare the CNC program that you measured the part as it came out of the CNC machine. You then measure the part as it comes out of the quench and temper. You compare those cloud maps, those millions of points of measurement, because people say, well, why do you need so many points of measurement? Well, you need so many points of measurement because you want to adjust that green size so that it will then come out to the desired final net shape, or at least closer to that final net shape. And as I said, we have a customer, we've done hundreds of these gears now over the last 5 years, and they don't have to do a final grinding process. They save $750 per gear by eliminating the final grinding process. They also save a week of time because the gears don't have to go to the grinder. They just put them in the machine.
You know, if I can stop you there for a second, I believe most of the companies have to go over the grinding process or, you know, correction process of heat treating because they do not have the R&D or they do not have the technology in order to fix that before heat treating, right? And the industry tends to believe that heat treating, right? And I heard this many. It is.
It has to be. It has to happen because the grains are changing size. But if you do it predictably and consistently, then you can manage it.
That was my next point. I mean, you cannot avoid distortion,
right?
But you can you can predict it or you can control it, right?
And manage it. Yes.
And manage it. You cannot eliminate distortion, but you can reduce it if you control it. If you I'm super thrilled about, to keep talking about this. I'm pretty sure we have a lot of material for a second podcast, but I wanna leave this one to quenching, right? We'd love to have another podcast with you. You know, I believe you're not only a heat treater, but you're a researcher. You're an engineer.
I have got, again, working with Professor Wallace, working with Lynn Ferguson at Dante Solutions, working with Dr. Cabasco. I mean, he's 86 years old this year. He's one of the shareholders of IQ Technologies. Dr. Cabasco has spent his lifetime basically in the quenching arena.
I believe that's correct.
He's not a metallurgist, he's a metallophysicist. That's what his doctorate's in, metallics, the physics of metallics.
So, I would love to have that guy on the podcast, I guess. If you can actually tell him that he's invited, if he would agree.
No one will understand a damn thing he says. That's the problem.
You know,
he basically, everything goes over everybody's head, and they say things like, well, that'll never work, or we don't understand, and their brains turn off.
Right.
But
so going back to quenching.
Yes.
Okay. We talked about basic quenching, well, and very complex quenching, but guys are measuring agitation and temperature, and you stated they're not getting the other half of the picture. You say you have to measure pressure, velocity, field boiling, and recirculation.
Right.
Did I miss something?
And uniformity of that. In other words, it can't just be a point of measurement over here in the tank. It's got to be, you've got to have a cloud map, essentially.
Right. So if we were to say that we had an instrument or that is measuring carbon percentage or temperature, or I don't know, like a high TC or gas levels, we should have the same computer, showing us temperature, agitation, pressure and velocity, film boiling potential, I don't know, you name it, recirculation and uniformity. If we were to do that, just let me finish there, Joe. If we were to apply that knowledge to heat treat, we could manage distortion. We can actually own distortion.
Yes.
Is that a fair statement?
Yes, that is a very fair statement.
And that's
we've been doing it commercially for 5 years now for a particular customer that basically dialed in their green size so that they don't have to grind the teeth on these big bevel gears, and they save $750 per gear.
Grinding and reworking parts, it's millions and millions of dollars of rework on industry-wise. So if you are halfway over there, I believe you. If you got something, you can capitalize it, you can monetize it a lot. So guys, if somebody's having distortion or grinding problems, just make sure you call Joe, right?
Well, again, but I also need somebody to make the proper, uniform, and consistent quenching equipment. You can't just do this in the standard quenching equipment that's been out there since my dad was quenching. It's not going to work.
And what do you think is that? Why do you think companies are not that interested to develop this type of technology, and they go to gas analysis or thermocouple technology, infrared technology? What do you think? Why do you think the heat box gets so much attention from heat treaters instead of the quench tank? Because there are very few guys like you. Everybody will be talking about the furnace, not the quench tank.
It should be called quench treating.
Quench treating.
Not heat treating, quench treating. That's what you're doing. You're quenching the part to get the mechanical properties. The heating is a precursor, but if you don't quench the part properly, what do you got? You don't have anything. So again,
it's like metal transformation process. It's like it's metal transforming process or something like that.
Yeah, we call it integrated heat treating solutions. Is called integrated because we are integrating the heating process with the quenching process with the inherent hardenability of the material. If you have a 1040 steel and you quench it in oil, you'll get 25 Rockwell. If you quench it in water, you'll get 54 Rockwell. What does that tell you about the inherent hardenability of 1040 steel? It tells you that it has a different inherent hardenability depending on the ability of the heat treater to harden it using a faster quench. And the faster the quench, the more instantaneous the impact is on the surface of that part, the more hardness and hardenability you will get out of a given alloy.
When I got this question to ask because I believe it's uh, you're gonna get very passionate about it. But when you go on
I'd have
heat treat
noticed that.
shops, I'm moving my hands now, just like you, right? But when you go on heat treat shops or when you talk to heat treaters, right?
Yes.
What are they getting wrong about quenching? Why do they forget?
Yeah, I'll send you the slide, but
Totally, we'll put
the
the slide.
slide basically says if you want to avoid distortion, if you want to keep a part from cracking, you slow down the quench. You go to a gas quench. You add alloying elements in the material so it has higher hardenability and it'll harden up in the gas quench. Now, Dr. Ferguson at Dante Solutions has created a gas quenching system that was the prototype is sitting at Akron Steel Treating currently. That gas quenching system essentially takes the hot part out of the furnace, and if it's a thin, let's say it's a thin ring or a thin helicopter gear that's hollow, and that gear has a flange on it with beveled teeth on it. Very thin, very complex part. When that part is quenched in a traditional high pressure gas quench, the nitrogen comes into the furnace and blows across the part with a 200 horsepower fan, let's say. That high pressure, high velocity gas traveling over that red hot part will make that ring go oval. His model predicts it, and it actually happens. So what do? They try to put fixtures on that ring to hold it. You cannot hold it because the transformations are happening inside the part. The transformations are happening at a non-uniform rate at the surface, and that translates into, like layers of an onion below the surface, into non-uniformity below the surface. And so what you end up with is an oval ring, and it's not round anymore. And if that ring has to have 60 thousandths of effective case depth on it, and you grind it into being round after heat treat, what have you done? You've removed most of the case on one part of the part, and you have more than enough case on another part of the part, and you may never get it to stay round, because as you're grinding it, you're also removing the stresses that are on the surface. And so the part continues to move around as you're grinding it because of that non-uniform shell that was created way back when in the quench. So what do? Dante has developed what's called the Dante controlled gas quench. The Dante controlled gas quench says, pull the part out of the furnace at 1950 degrees Fahrenheit, put it into this quench unit, which is a combination of temper furnace and chiller, and then you mix the gases that are running around and blowing over the part so that the initial quench goes from 1900 to 1500 degrees Fahrenheit as the door closes. The part then cools so that the thin and thick sections have now thermally shrunk at about the same rate to 1500 degrees. You then go to the next step, which is slightly above the, might be 1200 degrees and then 800 degrees. But nonetheless, you then mix hot and cold gas and blow it across the surface of the part so that it very slowly comes down. The thick and thin sections come down uniformly. Then once you're right above the Martensite start temperature, let's say 800 degrees Fahrenheit, you then again start quenching at 800 degrees Fahrenheit and then hold it till the thin and thick sections transform, create that shell on the outside of the part. And no matter what the geometry is, guess what's going to happen next? By conduction, it's going to predictably transform the hot core through the cold shell. Once that hot core converts like layers of an onion uniformly and predictably, you now have a part that has transformed with predictable size change. If you like the size change and you like the geometry that you got, fine. If you don't, adjust it up front in the green size before you stuck it in the furnace.
That's
Again,
amazing. I mean, that's a dream of every heat treater, I guess.
yes, it is the dream of every heat treater. And we're sitting on these two technologies, gas quenching and what I call high pressure instant impact water quenching, which are on two ends of the continuum, but they both do the exact same thing. And that is create that uniform shell, just like a salt quench does. When that part hits the hot molten salt, what happens? It creates a shell on the outside of the part. And then that shell controls, like layers of the onion below the surface, the conduction of the heat from the core out to the surface. And so it's not new, it's just a new way of looking at it. We have to remove our blinders and say, okay, water quenching is not a bad thing. It just has to be uniform and it has to be intensive. If it's uniform but not intensive, you're not going to get the same result because you don't build the shell fast enough. If it's intensive but not uniform, you're going to blow the part up. And Professor Wallace was right. It'll blow up.
Yes. It's been a ride talking to you, Joe. I hope it's not less of the time we talk on the podcast, because I believe you have a bunch of experience, a bunch of knowledge, and a bunch of things to share with the heat treat community, right?
Well,
These
I've been at it. I've been at it since I was 11 years old. I learned my Christmas gift money by raking parts in a shaker hearth furnace when I was 11 years old. So, you know.
It is, and you're very passionate about the industry, and this is what the industry needs. So that's what we're trying to do. We're trying to form a network of heat treaters that like to talk about this stuff, because you cannot talk. I mean, you have you're having like a dinner with friends and stuff. You cannot talk about this. Nobody's gonna understand anything.
No,
right?
Correct.
But
correct.
if you were to invite to dinner to heat treaters, I mean, these things will get very passionate, right?
Yes, yes.
And maybe with metallurgists, you will have a new rule: do not talk about religion, politics, or water quenching at the table, right? Because that might not work, right? But
Right.
but taking all your experience, all your passion, just to close the show. It's been a great show. I wish we could actually last longer, but
Thank you.
let's do a second one.
Thank you so much.
Let's do a second one in the short term. But now to close the show, you've been very passionate about this. You've been researching a lot. I'm pretty sure you have heat treated a lot of parts, a lot of stuff on different process, oil, gas, salt, polymer, you name it, right? But you have had your failures, your wins, your happy days, your sad days, that actually formed what you are today. But if you were to give an advice to a young engineer that wants to start on heat treating, what it would be? If you were to travel back in time and give an advice to your 30-year-old self, what it would be? That it's but don't say to measure in something else regarding temperature on the quench tank and flow.
Yeah. No, I think if I had my daughter is an engineer from Ohio State University. My son is an engineer from University of Mount Union here in Ohio. And as engineers, you need to understand that you learn more from your failures than you learn from your successes.
I love that.
Your successes hide the probability or possibility that something could have went wrong. It didn't go wrong, so you didn't address it. Whereas a failure, there it is. It's a failure. Now, why did the part blow up? Why did the part crack? And if you can determine that and then you can then prevent it, you've learned something and you can move the technology forward. And that's literally what we've been doing since Michael Aronoff did his presentation to Professor Wallace, who said it would never work. We proved that it did work. And in fact, Professor Wallace became one of our major supporters before he passed away. So at the end of the day, don't be afraid to fail. Learn from your failures, address your failures, and you will find that you have a more fundamental understanding. And that's really what technology transfer is all about. You have to thoroughly understand where you've been And then you have to thoroughly understand what happens when something goes wrong. And then you have to take that and learn from the failure and turn it into a success.
I love that. Don't be afraid to fail. This was Joe Powell, president of Acorn Steel Trading. Uh, Joe, I really would like to have a second episode with you. You know, I think you
All
have a
right.
bunch
Very
of
good.
knowledge. Just would like to remind the audience, we're posting weekly Heat Treat podcasts with experts on the subject. You saw the level of expert that we had today. Things got pretty technical. Thank you. So, Joe, one last time, help me with your hands. Go like this, because we're going to put the subscribe button over here. Go like
Okay.
this. Please subscribe to the channel. Give us a like,
Yep.
right? And we'll see you next week on the Heat Treat podcast. Have a great week.